in the first vertices position that we have for this selected object. I'll remove these two lines, create a new variable called new pause, short for new position, then use the new function that we learned, getVert $.mesh the first vertice, and then use here, instead of this position, the variable holding our position, new pause. So we get a 0.3 value from this function, put it in the variable, then use that variable to feed a 0.3 value into the make single tree function that we created. I'll save the function, then evaluate it so that it's reinstalled in the system, minimize the script, then run it. Well, it certainly did create a tree, but it doesn't seem like the tree is on the right spot. If the first vertex is actually on the plane, then this tree is really off. The reason for this is that the geometry data held by the .mesh property of the 3ds Max nodes is always in the local space of the object. What does that mean? Well, look at it this way. It has the data as if the object's pivot point was the origin, or in other words, the object's transformation is not applied to the vertex positions in this mesh that we get from the .mesh property. Basically, the tree would be nicely on target if there was no position, rotation, or scale data on our plane, if it had no transformation at all. This is actually logical if you think about it, since the positional, rotational, or scalar transformations of the object don't have much to do with the modifier stack from which we are getting this .mesh data. They're coming from a totally different pipe, the controllers assigned to these tracks. The modifier stack and its modifiers don't know about where our object actually is in the scene. They operate on the mesh in a local space, then at the very end of the object evaluation, the end result of the modifier stack gets transformed by the motion controllers into the proper place. Think of it like this. All the modifiers see the object's geometry as if it was in the origin, without any position, rotation, or scale applied to it. This is why we can actually take a box, for example, bend it with the bend modifier, then move it around in the scene and the bend effect will not change. For the bend modifier, our position offset movement didn't happen. It's still working on the object as if it was in the origin, so its effect will not change. We only changed the transformation of the object. The modifier stack didn't even note that. So again, the vertex position values that we just got are in this local, non-transformed coordinate system. How does this information help us? Well, since we now know this, we also know that if we want to get useful world space vertex positions, we have to apply the object's transformation to the vertex data ourselves, thus transferring the local space information into world space. Sounds pretty hardcore, eh? To get the transformation of the object, we'll just use another basic inherited node property, .transform. This property holds a matrix. To apply this transformation to our vertex data, we just simply have to multiply the vertex position with this .transform value. Let's see this in action. So let's go back to our script. Yeah, we are getting the vertex position here, but if you remember, this is in local space, so we will just use new position equals new position times the transform property of the selected mesh. As I said, multiplying by this transformation matrix is going to transform our 0.3 value using that offset transformation. Matrix math is in its own way pretty awesome. A simple multiplication will transform our data from one coordinate system to the other. If you're curious how and why this is, or what matrices are, well, keep listening. If not, just skip over this part. A matrix is a simple mathematical term to define a block of numbers. This might sound too simple, button.